what have we discussed? What we have discussed is that if we look at 1D steady state, that is a plane wall, right? We can come up with a concept of thermal resistance, right? And then we apply this concept, and the thermal resistance was defined as delta T over Q. Do I need any sign in there? No, right? Because we just know the way heat flows, right? That's the same reason they don't put like signs on the resistors here or anything like that, right? And this way we defined also this concept that was, which was, sorry. We defined that. It was a pretty cool concept because if the wall is thin compared to the width and the height, it doesn't really need to be plane, right? As long as the curvature is smooth compared to the thickness. So for that reason, we can say that a coat around you, right? My shirt here can be considered a plane wall. Although it doesn't look all too plain to me, but right? If from the point of view of calculation, you say it's plain, and you are going to be quite okay. And so we established some interesting thermal resistances. Anybody remembers the thermal resistance of conduction of a plane wall? Conduction is L over K, right? And we also talked about the thermal resistance of convection that was 1 over H, right? And then we said, how interesting, because what we call convection, right, it would have a thermal resistance of convection. In reality, it's a lie. The truth is there is conduction through a boundary layer, right? In reality, what we have is thermal resistance of conduction. And we said, okay, so if what we call 1 over H in reality is L over K, that means that we have a boundary layer of a thickness, and the thickness was K over H. Did I say it right? Yes. And I gave you some ballpark values, right? And we came up with some estimation of some estimate of the thickness of the boundary layer, right? Does anybody remember the thickness of the boundary layer in natural convection? 3 millimeters, give or take, in air, right? And if it is forced convection in air, is 0.3 millimeters, right? And the reason I'm talking about boundary layers now and about this relationship between conduction and convection is because in reality, convection is nothing but understanding if you have a thick or a thin boundary layer, and that's what that tells you how much heat you're going to lose. That's why if you have wind, the boundary layer gets thinner, therefore you lose more heat, right? And that's why a windy day is colder than a warm day. And that is also why swimming at 20 degrees is a lot colder than hanging out at 20 degrees air. All right, so we also made the equivalence for radiation, right? This would be H of radiation. What was the point of this? Oh, we talked about fins, and I wanted to tell you something about fins. Then we talked about thermal resistance of fin, right? Of one fin. And I told you it was tabulated. It was 1 over H area of the fin efficiency of the fin, right? And here, in this graph, you see how the efficiency of the fin is tabulated based on some parameters that are, here it says LC, and LC, here it tells you. So you just have to know how to read this. I'm not going to worry about details now, but I wanted to show you how the efficiency of one fin is tabulated. And somebody had too much time and calculated it. What if it is triangular? What if it is like a parabolic? What if it is rectangular fin? What if it is a circular fin around the tube? This is the typical case of many heat exchangers, right? For example, some AC systems, you're going to see that they have this tube with these fins around. Here you calculate the efficiency based on this parameter, which is just by looking at the figure. And oops. And then we talked about a set of fins, and we said it's 1 over H, A total. So A total was the area of the whole set of fins, and this efficiency of the set of fins comes from this formula. I'm not going to worry too much about that right now, but I wanted to show you, that's all I'm doing at this stage. I'm showing you how, even if you have a geometry as complex as a set of fins, you can calculate it very easily with no differential equations, no nothing, by plugging and chugging, right? This is the area of one fin, this is the total area. This is the efficiency of one fin that is tabulated here. So with this, you can do many calculations. What I want to do today is get into some calculations using these equivalent circuits, which are a lot simpler than this, right? Something else I mentioned by the end of last class was that if we have two types of circuits, how we would calculate the efficiency. So imagine we have two resistors in series, R1 and R2. What is the total resistance in this case? R1 plus R2. Okay. This is undeniable. You went through this. All right. So if you were to have a parallel system, what is equivalent resistance now? So the way I remember it is R1 to the minus 1 plus R2 to the minus 1, and both to the minus 1, which ends up being 1 over what you mentioned, right? So what happens in this case? How do we tell a series circuit? What is the criterion to say these two thermal resistances are in series? What is the criterion? The same heat flows through both of them. For example, I have my shirt and I have convection, right? Even without shirt, I'm not naked, right? Because I have this invisible jacket of still air, right? So now the heat from my body goes through the shirt, and the same heat goes through convection. So the conduction through the shirt and the convection to the air, those are two resistances in series, right? Okay, good. The condition for parallel is when the heat takes different paths. For example, you want to calculate how much heat do you lose in your house. You'd say I lose some heat through my window, and I lose some heat through the wall. That is different material, different insulation. So now you have two parallel paths. One path is the window, other path is the wall, right? And so how would you calculate the heat loss by your house? You calculate the resistances, and then the total resistance you calculate this other way.